HYPOTHALAMUS Artificial Intelligence, HAI, and the Research Center for Advanced Decision Technologies, RCADT, a private graduate academic center that uses artificial intelligence to complement advanced professional training, are pleased to invite you to watch the plan of the course, Smart Grids Optimization. The key milestones of Smart Grids origin are: 2001, the Electric Power Research Institute, EPRI, in the U.S., formally proposed the idea of a modernized grid that would integrate information and control technologies. 2001 to 2002, the Telegistor project was launched in Italy by the company Enel, considered the first large-scale commercial deployment of smart grid technology in homes, installing millions of smart meters. 2003, the Great Blackout in the Northeast U.S. and Canada acted as a catalyst to accelerate research into more resilient and digital grids. Smart grids gave rise to the concept of the Internet of Energy, which is currently experienced in developed countries. The course consists of 10 classes, which must be studied in 10 weeks, one per week. However, being virtual, the speed is defined by the student. For those who wish to do so, in addition to the course, RCADT offers advice on research and on the development of conceptual terms of reference for a specific project. Working with hypothalamus. Professional Services Methodology. The course is part of the group, Holistic Optimization of the Electric and Gas Sectors. Hypothalamus Artificial Intelligence, HI, has more than 50 years of experience in applied operations research and engineering consulting for the energy industry. HI and RCADT courses can be used as advanced consulting for professionals working in the sector who have not studied optimization and/or artificial intelligence, thus improving the knowledge they need in this new era. Originally, a power utility's decision support systems were conceived as composed of multiple mathematical models, one for each technical problem, which were operated individually and communicated sequentially by humans. The clearest examples were the models of economic dispatch and unit commitment, which today have evolved towards competitive, Nash-Carnot type, and regulated dispatch models. This way of operating produces solutions closest to optimal, but not optimal, because they generally have no feedback. The course is aimed at professionals interested in applying advanced optimization models in the energy sector and learning about the technological evolution, based on the power of computing, that is changing the way we use artificial intelligence and mathematical programming, making previously learned concepts obsolete. The academic program has been designed to strengthen analytical, technical, and managerial capabilities using scientific methodologies and artificial intelligence tools. This academic program has been designed to strengthen analytical, technical, and management capabilities in the power sector through the use of scientific methodologies and artificial intelligence tools. RCADT invites you to consult the virtual conference plan, integrated with artificial intelligence, of the latest version of the course Holistic Optimization of the Electricity and Gas Sectors. The course is divided in 3 modules: System and Markets, Smart Grids, and Advanced Modeling. The impact of smart grids and the Internet of Energy on artificial intelligence is very large. The consequence of this is to solve new mathematical problems through artificial general intelligence, that does not require centralized solutions or human participation. In 2014, IBM estimated that companies in the energy and utilities sector, which used big data and analytics, reported 23 times higher productivity than those that did not. HYPOTHALAMUS Artificial Intelligence, HAI, and the Research Center for Advanced Decision Technologies, RCADT, a private graduate academic center that uses artificial intelligence to complement advanced professional training, are pleased to invite you to watch the podcast of the course, Smart Grids Optimization. Operations research uses the scientific method to address organizational problems, focusing on providing management with a mathematical basis for decision-making. It is not a science, but more the application of science, logic, mathematics, statistics, and various theories to managerial and administrative problems. It focuses on organized systems, using interdisciplinary teams of scientists and engineers. Operational research began in 1937 in Britain and developed in countries such as Australia, Canada, France, and the United States. Aimed at Professionals, engineers, mathematicians, physicists, consultants, economists, data scientists, software developers, etc., who require and or wish to know mathematical modeling, advanced analytics algorithms, related, among others, to the implications of Industry 4.0 and its relationship with the process of evaluating the technical economic impact of the decisions that are made. This continuing education program strengthens the analytical skills and professional criteria of the participants, so that they can exercise, share and or supervise, with propriety, the professional functions in accordance with the state-of-the-art of the methodologies and technologies that support the digital transformation of the companies. Mathematical methodologies. Mathematical methodologies correspond to the scientific foundations for implementing mathematical optimization models. Specific objectives: training in fundamental methodologies to support modern mathematical modeling. To train so that the mathematical modeling of industrial and business processes is a generator of real socioeconomic wealth frequently used in our society. Understand that optimizing the use of resources is the scientific basis of sustainable development. Learn about systems and industrial market modeling. Learn the fundamentals of modeling real problems based on the integration between mathematical models and data models. Information technologies. Computer technologies correspond to the computer tools available, freely or commercially, to design and implement solutions to problems in social or industrial organizations. Specific objectives: learn how to implement solutions applied in the real world by making use of the modern computer technologies available for the algebraic modeling of industrial and business systems. Present and manage live tools used by large companies to solve their optimization problems. Understand the state-of-the-art of optimization and its relationship to smart computing. Know the available technologies, as the principle of basic knowledge to be able to solve, in reasonable times, problems with millions of variables. Know the fundamentals that must be had for the assembly of models using the most effective technologies. Economic dispatch models. The history. Perhaps the first type of algorithm to solve the problem from dispatch to economic was dynamic programming. Dynamic programming, DP, is a numerical technique for solving complex problems by breaking them down into simpler, overlapping subproblems, storing their solutions in tables, to avoid redundant calculations. The term programming in this context refers to mathematical optimization, not computer programming. The problems were faced as either deterministic or stochastic. Because it is numerical, there are many variations of the algorithms. Problems were solved based on a monolithic solution of the entire system. Taking advantage of the popularity of commercial algorithms, mathematical programming replaced numerical versions of dynamic programming. Problems were approached deterministically and solved based on a monolithic solution, implying a centralized approach. The realism limitations of deterministic mathematical programming was the starting point for incorporating large-scale optimization methodologies to solve stochastic programming problems. In these methodologies, Bender's theory and Lagrangian relaxation stand out. Conceptually, the two methodologies are similar. In general terms, problems are divided into two levels, the upper one related to the coordinating problem, and the second level with its slave problems associated with combinations of dimensions of decomposition. In the example, the subproblems are associated with the smart grids that must be coordinated. These methodologies are a solution method that allows parallelizing the problem and accelerates its solution time. However, the problem is solved monolithically, that means centralized. Smart grids, the Internet of Energy, and Industry 4.0 have brought about a fundamental shift in the mathematical approach to solving problems, giving rise to consensus algorithms to address the solution, as they do not require centralized solutions or human intervention. The rules of consensus are based on mathematical laws, such as the theory of duality. The consequence of this is to solve mathematical problems through artificial general intelligence. Distributed economic dispatch. Distributed economic dispatch, DED, is an optimization model in smart grids that seeks to allocate energy generation at the lowest possible cost without depending on a centralized control center. In this system, Each generating unit acts as an intelligent agent that makes local decisions and communicates only with its neighbors. Unlike the centralized model, the system is represented by a communication graph, where the nodes are the agents and the arcs are the data links. Important concepts in DET are consensus variables. The key concept is marginal cost. The system reaches the economic optimum when all generators operate at that level. Information mechanism. Agents use a consensus algorithm to estimate the overall miscoordination between supply and demand, based solely on information from their immediate neighbors. Topology. This can be a bus, ring, or mesh network, and the model must be robust to changes in topology, such as link failures or cyberattacks. The overall goal is to minimize the total cost function, subject to power balance constraints and capacity limits. Consensus algorithms are fundamental to the operation of decentralized networks, mainly blockchain networks. They ensure that all network participants agree on the validity of transactions and the state of the blockchain. Without consensus, there would be discrepancies in the data between different nodes, which could lead to fraud and errors. These algorithms facilitate trust between users who may not know or trust each other, allowing decentralized systems to function effectively. Different consensus mechanisms have been developed to respond to the needs of various applications, each with its own strengths and weaknesses. Validate transactions and add them to the database. Prevent double spending and fraudulent activities. Improve network security against attacks. Optimize network performance. Allow decentralized decision-making. There are several types of consensus algorithms, each designed to address specific needs and challenges within distributed and autonomous network technology. Each type employs different mechanisms to achieve consensus, thus influencing the overall efficiency and scalability of the network. Understanding the particularities of each can help determine which one is best suited for specific applications. The most widely recognized types are: proof of work requires participants to solve complex mathematical problems. Proof of stake allows validators to create new blocks based on the power they possess. Delegated proof of stake involves selecting some nodes to validate transactions on behalf of others. Practical Byzantine fault tolerance errors focuses on achieving consensus despite failures or malicious actors. Proof of authority relies on a limited number of trusted nodes to validate transactions. The importance of consensus algorithms cannot be underestimated, as they provide the backbone for the reliability of autonomous and distributed networks. They ensure that all participants maintain a unified view of the network, which is essential for transparency and accountability. These algorithms protect the network from various types of attacks, such as Sybil attacks, where a malicious actor creates multiple identities to take control of the network. The choice of algorithm can significantly affect the speed and scalability of transactions. Therefore, selecting the right consensus mechanism is a critical factor in the design of a decentralized system, because they establish a safe and reliable way to reach an agreement, minimize the risk of network forks, which can lead to confusion, allow the system to function without a central authority, dictate how quickly transactions can be processed, and influence the costs associated with maintaining the network. While consensus algorithms are essential, they also come with their own challenges. A major issue is scalability, as many algorithms struggle to efficiently handle a growing number of transactions. Some consensus mechanisms, such as proof of work, POW, have been criticized for their high energy consumption and environmental impact. Security is another concern, as vulnerabilities in the algorithm can lead to exploitation and attacks. Achieving consensus in a decentralized environment can introduce latency, affecting the overall performance of networks in real time. These challenges require continuous research and innovation in the field of consensus mechanisms. Some problems to be solved are: scalability issues can lead to slower transaction times. Energy consumption is a significant concern for POW systems. Security vulnerabilities can expose the network to attacks. Latency can affect the user experience during high traffic periods, and continuous improvement in algorithms is necessary for adaptation. The future of consensus algorithms is promising, with continued advances aimed at addressing current limitations. Innovations such as hybrid consensus models are emerging, which combine diverse algorithms to leverage their strengths while mitigating weaknesses. Research on more energy-efficient consensus mechanisms is gaining traction, focusing on sustainability. As autonomous networking technology evolves, we can expect a greater emphasis on scalability and speed, ensuring that decentralized systems can compete with traditional centralized solutions. The development of new consensus algorithms will play a key role in shaping the future landscape of autonomous networks. Hybrid models can enhance performance and reduce energy use. New protocols are being developed for faster transaction times. Research into quantum-resistant algorithms is on the rise. Community governance may influence future algorithm designs, and the integration of artificial intelligence may optimize consensus processes. Consensus algorithms are vital to ensure the reliability and security of real-time networks, such as smart grid networks and blockchains, as they facilitate agreement between decentralized participants, enabling transparent and reliable transactions. While challenges remain, innovation still promises to improve the scalability, efficiency, and sustainability of networks in real time. As the landscape continues to evolve, understanding these algorithms will be essential for developers, users, and stakeholders in the distributed operations ecosystem. In smart grids, consensus algorithms are used to coordinate distributed decision-making among multiple agents, like smart meters, microgrid controllers, distributed generators, without relying on a central authority. They are crucial for distributed energy management, economic dispatch, voltage/frequency control, and peer-to-peer energy trading. Byzantine fault tolerance, BFT, is the ability of a distributed system to reach a reliable consensus and continue to function properly, even if some of its components fail, or act maliciously. This concept is derived from the Byzantine general's problem, an allegory where generals must agree on a common strategy, attack or retreat, even though some may be traitors who send contradictory information. One of the clearest and most fundamental implementations of BFT is the practical Byzantine fault tolerance, PBFT, introduced by Miguel Castro and Barbara Liskov in 1999. The figure shows an example of a relatively simple grouping of Byzantine fault tolerance, BFT, consensus algorithm. Let's imagine a group of nodes where one acts as the leader and the others as backups. The process follows three main phases. Pre-prepare. The leader receives a request from a customer and assigns it a sequence number, sending it to all nodes to let them know which transaction is next. Prepare. Each node receives the message and forwards it to the others. This serves to confirm that everyone agrees on the order of that specific transaction. Commit. Once a node receives enough commits from its peers, typically a majority of 2 out of 3, it sends a final message to inform, "I'm ready to register this." The system tolerates up to 1 in 3 failed or malicious nodes. If the leader tries to trick the network by sending different sequence numbers to different people, the nodes will compare their messages in the prepare and commit phases, detect the inconsistency, and simply ignore the leader or remove them. 3 stages make up the process. Group the nodes participating in the consensus. Elect a leader, and communication process, within the group and among the group of leaders. All nodes are selected as different levels, and different levels may have different tasks. After the levels are divided, different levels cooperate with each other to reach a final consensus. High power. The coordination of 2 types of models is studied. Economic dispatch and unit commitment, and competitive electricity markets, distributed economic dispatch, electricity system and wholesale market optimization models. Make up a flexible decision support system that provides different types of services in an integral way. They can be classified into integrated dispatch of generation plants, optimization of generating agents, and predictive analytics of stochastic processes. High power is a decision support system that has been developed to support the decision-making processes of agents participating in the electricity and/or natural gas markets. High power is composed of a set of optimization models that describe the supply/demand process of electricity and natural gas. From this point of view, It determines the partial equilibrium point of the electricity and gas markets under conditions of economic efficiency. Four models are considered fundamental to support the strategic, tactical and operational decisions of an agent that operates generation plants. High power is built following the principles of structured mathematical modeling, which are specific to optics. Under this conception, software is built by means of layers of equations, which are integrated to build the models, which are part of a decision support system. In the case of high power, it is an economic dispatch model, typical of the electricity sector. The diagram shows 8 of the many models available at high power. Any of the models can be run in their deterministic or stochastic version, making use of asynchronous parallel optimization. Operational planning and unit commitment. A well-known activity in the electricity sector is the coordination of two fundamental models: economic dispatch, or operational planning, DP, and unit commitment, UC. Electric transmission network connectivity based on the detailed connectivity of the electricity transmission system using bars and circuits. Below, we will briefly and partially discuss HY's philosophy on the operating models it has used so far in the power sector, which can be used for an isolated smart grid. But with the arrival of Industry 4.0, technological change led to smart grids being considered autonomous and independent networks, which totally changes the modeling paradigm, considering that today there are no longer monolithic electrical systems. Attempting to model a smart grid network with traditional dispatch models is a major mathematical error. First, its size would be unmanageable in data and computer processing. Second, mathematics has changed to adapt to this new era. It makes no sense to use outdated mathematics, and third, it may be most important, it violates the philosophy of the new business and its regulation. All the models and methodologies developed for the electricity system and the wholesale market are applicable to smart grids, when analyzed as an independent system. It's just a problem of scale. Unit commitment, UC, associated with short-term operational planning decisions, such as the optimization of detailed distribution by the hour or for shorter periods, respecting all the constraints of the nonlinear and discrete system. The UC model is a mathematical problem that can be converted into nonlinear non-convex mixed optimization, which implies that it requires a special effort for its solution, since its real-time characteristic does not allow unfeasible approximations for its solution. On the other hand, it is necessary to coordinate the UC model with a medium-term planning, DP, model, which establishes the boundary conditions, in such a way that the state of the system at the end of the UC problem be the same as at the beginning of the DP problem. Below, we will briefly and partially discuss HY's philosophy on the operating models it has used so far in the power sector, which can be used for an isolated smart grid. Ideally, a single model should be solved, which would allow the system to be represented in detail throughout the planning period, that is, solving a long-term scheduling problem during periods 1 to t. For complex systems, this may not be computationally viable. However, for not-so-complex systems the alternative could be viable, considering the computational capacity offered by Industry 4.0. For this reason, conventionally it has been considered necessary to resort to the integration of both models, UC and DP. You should consider the implicit approaches involved in such a decision. Based on the vision of the artificial hypothalamus, building a monolithic model consists of cutting and pasting equations, and thus obtaining the optimal solution, regardless of the type of dispatch model that is appropriate according to the market. The solution of the monolithic model can be realized with large-scale optimization methodologies. The traditional thing has been to divide the process into two models. Stochastic economic dispatch model, oriented to planning activities, and deterministic model of unit commitment, oriented towards real-time scheduling. The coordination of both models is essential for the results obtained for the real generation. The traditional way to approach the problem is to coordinate the two models, solving each independently, offline, so that the office planning model, DP, establishes the boundary conditions of the office scheduling model, UC, which can be interpreted as the optimal planning objectives. This approach may not have a viable solution in the UC, because the differences and/or approximations could lead to the non-viability of the set of objectives established by the DP for the UC. There are two alternatives to carry out coordination. Coordination through economic variables, dual variables or prices. To this end, the opportunity value of inventories is set at the end of the period TCP, or at the beginning of the first period. In this case, it corresponds to the value of the water. The application of this approach should be careful, as boundary conditions should reflect variation in prices between periods, but in general, only a sample of the value of water is considered, at the beginning or at the end of the planning horizon. This can lead to water value profiles, which are far removed from the profile estimated by the DP model, which is never observed in the UC. This approach always offers viable solutions, but they may be far from optimal due to the distortion of the dynamic price profile. Coordination through physical variables, primal variables or quantities. To this end, the quantities of resources to be used and the quantities of industrial products to be produced during the period of operation of one to the same period are established. The inventory levels that must be reached at the end of the period, the TCP moment, are also established. This approach does not distort the dynamic price profile but may not have a viable solution due to the small differences between the two models. Non-feasibility, which can be managed by soft constraints, which introduce penalized slack in the target function, to ensure that the final schedule is close to the optimal target set by the planning. The chaining, or coordination, of models does not guarantee optimality, because there are always at least two alternatives to concatenate two models. By quantities, or primal variables, such as water use, or resource use in general, or by prices, or dual variables, that is, the value of water, or in general the value of resources. Cyclical coordination can produce the optimal solution, or correct unfeasible solutions. The integrated model can be solved using large-scale techniques, such as Bender's partitioning and Lagrangian relaxation. This approach reduces solution time and memory requirements. Operational planning and unit commitment. A well-known activity in the electricity sector is the coordination of two fundamental models: economic dispatch, or operational planning, DP, and unit commitment, UC. Each smart grid requires a specific decision support system that allows the operator to interact with the entire electricity system. Starting from the original electrical system, a wholesale electricity market. Smart grids were advancing little by little, initially seen as isolated systems. Currently, these electrical systems must coexist and interact with each other. The centralized control of the system focused on the development of assets, hardware and software, for the wholesale electricity system. The emergence and development of smart grids generates a distributed control of the system, in which many islands, which initially operate in isolation, must be coordinated. Technological evolution has given rise to total distributed control, in which multiple types of electrical assets coexist and communicate with each other. Smart grids have generated communities of users that consume and generate energy and require a broad control system that unites all the production-consumption cells that the electricity system has. It is a system like the Internet, where the autonomous communities share physical resources and communicate with each other, which gives greater power to the physical system, but requires more advanced artificial intelligence to manage it. Under the concept of OpTeX, Optimization Expert System, the software is built using layers of equations that are integrated to build the models. The current models of dispatch planning, DP, and unit commitment, UC, can be used for current smart grids, making the necessary scale and regulation adjustments. Autonomous real-time distributed economic dispatch. Challenge: modify the traditional centralized economic dispatch through a distributed economic dispatch to enter the Industry 4.0 environment. Solution: it implies that all agents must know what information they need to take from smart metering systems, and what information they must provide to other agents to make their decisions, to keep the end-to-end system on the optimality path. This is possible using asynchronous parallel optimization methodologies. Methodology: in the case of regional smart grids, the process of planning or scheduling electricity systems could be carried out as follows. The connection topology of smart grid networks is developed according to the criteria of a central coordinator, the regulation, and/or the autonomous decisions of the agents. The mathematical models running on each smart grid correspond to the currently tuned models, DP and/or UC, but in general they are the same models that are currently used. The adjustments of the models are related to scale or regulation details. This network does not require a physical coordinator, as the models run independently on each smart grid and coordinate autonomously, and the coordination of the models can be done by prices or by quantities, which will be the consensus methodologies. The two methods of coordination are valid mathematical methodologies, either by prices or by quantities. The system coordinator must choose one of the two. Perhaps it is better that it is regulated, because all smart grids must coexist autonomously and independently in the same region, but following game rules. Coordination by quantities is more complicated, because it is not a variable common to the subsystems. Coordination by prices seems easier and is a well-known rule in economics. Optimal marginal costs, without restrictions, must be the same in all smart grids. This is a consensus scientific rule, which has been well studied and cannot be questioned, since it is not an opinion. This is High's proposal. The solution of the UC or PD problem is independent of the conception of the distributed dispatch system. Within each smart grid, the optimization problem can be solved monolithically or use large-scale optimization techniques, such as Bender's and Lagrange's decomposition theories. Models with different methodologies, or technologies, of solution can coexist. The graph presents a topology composed of two groups of smart grids and a large generating plant, and a wind farm. The approach can be conceived as an artificial brain composed of a network of mathematical models, a model for each smart grid and for each site of large generation and/or consumption. Communication between the algorithms of mathematical problems must be asynchronous when events occur in the system. This can be continuous. For optimization purposes, the artificial brain does not need a coordinator, as the smart grid system acts autonomously and independently. However, in order to function as a technical control and regulatory control, it may be necessary to have a system supervisor. The course group director is the founder and executive director of RCADT. Engineer Velázquez Bermudez's experience in applied operations research dates back to 1972, which means that he has accumulated 50 years solving real-world problems doing engineering consulting using mathematical models. RCADT is the most applied academic center in the integration of the teaching of mathematical programming and artificial intelligence. For more information you can consult the URL. Remember, all science as it grows toward perfection becomes mathematical in its ideas. Alfred Whitehead. Thank you very much for your attention.